Yeah, so today I'm mostly going to present the work carried by Axel, who's a grad student with us, and with Gordon Watstein at Stanford. And it's the result of great collaborations over the years with many great people. So Nina Miolan, who's now at UCSB, Julien Martel, who's now in a startup, but who was really instrumental in getting the ideas and the concepts. Youssef and Ariana at LCLS at SLAC for the implementation, the early implementation. And yeah, the support of Mike Dunn, who's the LCLS director. And recently, collaboration with Ellen, so I'm going to talk a little bit about that. You heard the big picture of CryoDragon on Monday, so I'm just going to zoom in a little bit on some little aspects. But yeah, so the idea today is to talk about amortized inference, and if you're not familiar with it, hopefully by the end of it, you'll have a picture of what that means. So, okay, that's probably the 10 times you hear what are we trying to do. So I'm going to try to go fast on this, but essentially, we have a bunch of images that we measured that we can model the formation of using a simplified image formation model that's usually pretty accurate for the type of experiment that we care about in Cryo-EM for single particle imaging. I'm not talking about Cryo-ET or more like complex imaging processes. And we know that in that model we have a few variables that we need but we don't observe. So for example, for each molecule that we image, we are interested in the volume of that molecule. That's actually what we want at the end. But each of those volumes is oriented in a pose that we don't know. We actually don't care about the pose, but we need it. Yeah, unless you've heard other talks that try to avoid it altogether, but in our case, we really need it. So going from the measurement to those variables is typical inverse problem that we're trying to solve. Okay, so in a little bit more detail about this image formation model, we have the pose, which is a rotation and a translation of the molecule. And then you can build the exact equation where you have to rotate your volume, you project it, corrupt it with the optical effect of the lens. For the whole talk, I'm going to assume that those are given. Maybe you didn't center your particle perfectly, and then you corrupt it further with a lot of noise. Okay, so we simplify back this equation now, and I'm going to rephrase this slightly differently by talking about the probability of the image given the model, right? And what we know is that we can write this probability and equate it to the distribution of the noise, and that allows us to basically draw a very graphical model that is on the left here, where you see that the image yi is conditioned on the existence of a volume V and a pose phi I. And in this case, I'm going to talk about homogeneous reconstruction, where the volume V is the same across the data set, right? We are not trying to have one volume per image. That comes later. Okay, so that's just remember the graph on the left, and that's all we're trying to do. Okay, so that's the forward model, and I said we wanted to solve the inverse problem. And the typical way to do this is to iterate through the steps that I'm going to take you through now. And this has been implemented in Cryo-EM, but also in X-ray single particle imaging, where essentially the algorithms are some flavors of expectation maximization algorithms, where you have first a pose search, which means that for the current estimate of the volume and the image at hand, you try to estimate the pose of the particle in the image. And then you back project with the current estimate of the pose and the data. You update your volume, V, and you iterate. And that's true in both fields. Well, today, obviously, we talk about Cryo-EM, but since I work for an X-ray facility, I had to mention the other one. So, contractually. So, there is several ways to do each of those steps. So the pose search, you could either say, I'm estimating exactly one pose for each image, or I estimate the probability over all the poses, which is multi-mode versus single mode. And in the back projection step, you can do several things. You can either back project until you converge, or you can just take a few steps and back. And that's how you can pretty much classify the different algorithms on the market. So for example, Relion is an example where when you do the pose search, you actually pose over all SO3, and then you fully maximize in the back projection step, which is the M in expectation maximization, in EM. At each iteration, CryoSpark took a different approach a few years after by basically just doing gradient descent at each step, which allowed to go for ab initio solutions. That's also the approach followed by CryoDragon 2. Yeah, and essentially what distinguished CryoSpark ab initio from CryoSpark refinement would be the way back projection is carried. That's one way to see it. So in all those approaches, the rate limiting step is the pose search. And the reason is that you have to do the pose search, you have to basically solve this problem, which is for each image, you have to compare it against all the possible poses that you can. So typically you would sample SO3 and compute the correlation and keep the best. So this is very expensive. It doesn't scale well. As your dataset size grows, it's going to be harder and harder. And it doesn't leverage the fact that very often you're going to see very similar images. So the noise will be different, but like you're going to see the same orientation a lot of times. And so that's where amortized inference comes in. So instead of doing this orientation matching for each of your images, you're going to train a function. You're going to look for a function that has parameters that you are going to learn. And once that function is trained, you're just going to ask it, given this image, please give me the pose. So you encode the pose from the image using that function. So you introduce a new variable in the problem, which we call psi here. But you make the problem slightly easier by replacing a very computationally expensive optimization problem into a training and evaluation problem. If done well, like the training could be complicated, but like that's the idea of amortized approach. And you amortize because at some point, once you know psi, maybe you'll know it in just a few iterations, and then you just need to evaluate it. So you don't need to go over the whole data set, for example. All right. So how does that change the iteration process, the algorithm? So we say that we have this encoding where we call the function psi for each image yi, and we get the pose phi I. So you could also do that in two different ways, in a non-variational way versus variational way. And then you still go back to updating your volume somehow, and that's here. Instead of back projection, I wrote back propagation, because you go through essentially your pipeline, your end-to-end differentiable pipeline to do that. And you update both your volume and your encoder, the parameters of your encoder psi. Right? And that you usually do but just by gradient step. That I don't think it would make sense to do otherwise. So, and then you iterate. And again, you can use this dichotomy to like basically sort out the different algorithms on the market. So yes.
So in this process, do you retrain your network?
Do you?
Retrain this network which finds points.
So in this process, initially the network would be like the weights and all that would be random, and then you would train it once.
But you retrain it in this loop.
So you update it. You update the weights every time you. So what I mean here by this red arrow is that you update the weights there in like a gradient descent way, right? You just update them. You don't retrain them from scratch every time. Right, so for those of you who are aware of this work from the DeepMind people, they would basically take a variational approach on the pose search. What that means is that they would not only estimate one pose for each image, but they would basically estimate the parameters of a distribution, typically a Gaussian. And so there are like pros and cons to do that. In CryoDragon 2, for those who paid attention, there is also an implementation of this that gave some artifactual results for the reason that I'm going to explain after. But that was also an implementation of a variational encoding. And then if you go the other way, I think the first to implement it was Cryo-OpenNet that we did last year, where you estimate exactly one, you use the encoder to estimate exactly one pose for each image. And now cryoAI. So I'm going to talk a little bit more about cryoAI. So Cryo-OpenNet worked on synthetic data and failed on experimental data. And Cryo, and that was kind of the impetus for us to look into this. We didn't really understand why. Maybe as a little spoiler, the reason is that the way we were, let's say, simulating the data that we were then training on, we were only exploring half of SO3, which means that we didn't have this problem in Cryo-EM that you don't know if you're looking at the object from above or from below, essentially. So that's what I'm going to spend a few slides explaining now, because it's simple, but it's actually, I don't know, I'm not sure I understand it very well, to be honest. Yes?
So just to understand, you build your training set on a small piece of the data by trying all poses, like Relion or CryoSpark?
Simulated data.
So the experiments that we did for Cryo-OpenNet, we generated a data set, and each image you would have to take it from a different pose, right? And the poses distribution that we have only covered half of SO3. We didn't go the whole way. And if we did that, it would have failed, but we didn't realize.
No, but when you want to run this on real data, eventually you will...
then it failed. We basically, it didn't work. Yeah, we got stuck into this the same artifactual problem as post-VAE encountered. So, right. So cryoAI implemented something that made it work. And I'm going to try to explain it now. But first of all, I described the iterative algorithm, so how do you actually implement it? So the approach that we followed was an Autoencoder architecture. So the encoder is here. So you start from a representation of your volume, and you go from there so it's a forward model, so you go from there to the image. So the first thing you have to do is to rotate the volume, and then you take the projection, and that gives you the image. So here we are also in Fourier space. It could be done in real space. It's just, in this case, we are in Fourier space. So that's our encoder, and I call theta the parameters of that encoder. Typically, you could think of theta as the values of the voxels in the map of V, if you represent V as a map, or if you represent V as a neural net, it would be the weights of the neural net, etc. So an autoencoder architecture is an encoder and a decoder. So the encoder basically takes an experimental image and encodes it, as I said, into a pose. And we call psi the parameters of that encoder. And the pose is made of a rotation matrix and a translation vector. So out of the encoder, we take that rotation matrix and feed it to the decoder. And the translation vector and the CTF are applied as well to yield the simulated image hat X, which we then compare to the Fourier transform of the experimental image. So typically, to compare them, you would take what's called the L2 loss, which is basically just the distance between the two images. And one image is the experimental image, and the other one is the encoded, decoded image, so the fake image that we generated given our weights psi and theta. And from that difference, we're going to backpropagate to update our parameter psi and theta, right? So you remember the iteration, and so now that we went forward, now we go backward by updating our weights, and we train and we train and we train until we converge. Once we have converged, we can just use our encoder as it is and just ask it on new data what is the pose, and that would work if the new data is similar to the data that we use for training.
Can I ask a question here?
Yes, please.
So can you have like leave out set where you measure your loss on the leave out set? Does that make sense here, or does it?
On the what?
So some images that you don't use in your training.
Left out. Okay, yeah.
Left out, yeah.
No, I didn't hear. Sorry. So you would train on one set, and so that's what you would do to evaluate, for example, whether you really converge, right? Yeah.
Do you guys do this?
Yes, to check. Yes.
Because I understood in CryoDragon it's not possible. You can't do this.
Well.
Okay, but coffee discussion.
No, I think you could. So you don't use it to train. You use it to evaluate whether the training is correct, right? Essentially.
Yes.
But yeah, it's like yes.
So just to be sure, the training data is simulated data or experimental data images from different datasets?
So in this case, it's here I show an experimental image. Earlier I mentioned fake data because we started with that, right? And first you want it to work on fake data, and once it works on fake data, then you move on to real data, and then it doesn't work anymore. And then you have to start all over again. So if there are, I know there are students in the room, always start from real data because you save a lot of time. That was advice a few years ago, actually. So yeah, it's much harder, but yeah. So yeah, so right, so that's the idea. The problem is, if you do that, then it doesn't work, and that's exactly what I want to talk about. The reason it doesn't work is that the problem is ill-posed in the sense that I'm going to explain. So let's call our data set this way, right? And what this means is that we have an ensemble of images that come from a volume that we don't know, and an ensemble of poses phi, right? And the L2 loss that I mentioned, if I describe it a bit more, looks like this. So if you minimize this quantity, you solve the self-supervised unknown view tomography problem, right? Because you don't know the views, you don't know the volume and you don't know the views, right? So it's really what we're doing here. And it turns out the solution to this is not unique. There are a bunch of ways to minimize this, and the different ways that I'm going to show are not compatible with one another. So the first type of ambiguity that we have is rotational, right? So here I'm showing the actual volume that we are looking for with the actual pose that we know it comes from. It turns out that if I give that as a solution, it will minimize my function. But if I take any other pose and I rotate my volume by that orientation, and I update my pose by multiplying it with it, it's also a valid solution, right? So there is an ambiguity there, and like the origin is not defined. So that's kind of an easy one. The harder one is the handedness ambiguity, and again, intuitively, you can really think of it as like Cryo-EM is a process of like orthoscopic imaging, so you don't have like lines that diverge, it's really like orthoscopic. And you're going through a volume that's not absorbing, so it's transparent, which means that you result with images that could result from looking at the object from above or from below. It's very hard to tell. So that's the intuitive aspect of this handedness problem, right? To be a bit more specific, I will need to define some stuff. All right, so let's talk about Euler angles. And let's say that we have oriented our space and we have a plane P that's in the x, y, and the normal to it is z, okay? I'm going to need to define what's a symmetric volume with respect to P. So it's pretty intuitive. It's basically, if my volume is V of x, y, z, the symmetric volume is V of x, y minus z, right? So it's like my hands, right? Symmetric pose, this one is a bit more difficult, but essentially, if this is one view here, the symmetric will be on the other side, viewed from the other way. I have a drawing after. I should have done this here, which means that the image that you get from a given volume and a given pose is exactly the same given by the symmetric volume and the symmetric pose. Okay, so that's for symmetry. Okay, so I'm trying to. Hopefully this is clear. If it's not, please let me know. Okay. The problem is, in reality, of course, we are not dealing with always symmetric objects, but turns out that most objects are symmetric enough that we are in trouble. In the sense that now if I look at this volume V here. So maybe now you don't believe me that it's pseudo-symmetric, but soon you might see it. It turns out it's very similar to, it's symmetric with respect to some plane that I'm going to have some trouble distinguishing images, right? So let me see if I can convince you. So here we're looking at this volume with two distinct cameras, right? The red and the purple. And right now they are in the same spot, so they give me the same pose, right? So this is the pose predicted by one and the other, and they agree if I compare my two images, they're going to look very similar, actually identical. Okay, so now I'm going to move one camera to the symmetric position. Okay, and turns out it's going to look at this object, and if the object was symmetric, it would return the other pose, right? Well, turns out if you look at this hand and you downsample it, you'll see that this is actually pretty confusing. It's very, I wish I had Roy's figures because that would help. But so essentially this is the heart of the problem, right? That basically the image produced by this camera is very similar to the image produced by this camera for this object because the object and its symmetric actually are roughly the same. So if we try to quantify that, the difference between those two images, we're going to get to the next slides. But basically here, I forgot I wanted to stress that. So volumes generally have pseudosymmetries, and that leads to pose ambiguity. So let's see at the quantification of it. So again, let's look at this pseudosymmetric volume here, and let's quantify the difference between itself and its image. And it's symmetric across this plane, right? I'm going to do this for all the plane P, right? So this is the current plane here, and here is a measure of how similar they are. So it turns out we are at the minimum right now, but I just want to convince you that this is a minimum. And why it leads to this ambiguity on the pose estimation. Now I'm going to rotate that plane and look at the difference between the two hands now. So you see that you can see already that it's very hard. It's much harder to confuse them now, right? They really look much more different. There is no easy way to say, okay, even if I don't sample one, I'm going to get that because you've got a lot of mass here that's not in the other one, etc. Right? And it's even worse if I go to that plane here because I have one finger that sticks out, and then I would have the figure at the other one. So it's also very hard to confuse the two. So this is really the plane where things get tricky, right? And that's usually where we're going to end up having problems. Particularly when we start amortizing, when we start like asking an encoder, the encoder will really probably have a hard time distinguishing those things, right? It doesn't have infinite power. Yes?
So isn't this a problem that all reconstruction algorithms face?
Yes.
And why do they work?
So the short answer is because they don't amortize and because they do systematic post search, which means that if you systematically go across SO3 and you don't just flow there, right, you might be able to jump to the right solution at some point, right? In principle, yeah. But it turns out that if you look at the CryoSpark, for example, process, or maybe Relion, early on, you'll end up with often something symmetric that will, and then you will escape from it because of this post-search mechanism. When you encode, when you amortize, and that's a problem that we encountered, you don't have this escape mechanism built in, and that's why we are building it. That's exactly what's going on, yeah. We have this collapse. So I'm going to call H that encoder. It's easier, right? So it takes an image and outputs a pose. And like I said, we have some ambiguities, right? Both of these solutions are valid, right? The encoder for a given pose will give me the pose up to a rotation, or it's symmetric up to rotation. And we said that it's perfectly valid. Both of them are right. The problem is that the encoder has no way to be consistent across the dataset. Sometimes it will give this answer, sometimes it will give this answer, and you end up with something that becomes symmetric. And usually with respect to the plane, that's the most confusing, like I showed before, right? So that's the result that PoseVAE gave in CryoDragon 2 paper. This is a problem that is recurring if you try to minimize the L2 loss with an encoder because of this handedness ambiguity. So how do you fight it? Okay, so we have established that this encoder H tends to be what we call P-ambiguous, right? So there is a plane P where it's very hard to distinguish a volume and it's symmetric. Okay, so it basically will give the same predicted pose for an image that would come from a given pose, or it's symmetric, and it would not, one time it would give this solution, sometime it would give the other one. It's not going to be consistent. So we want to find a new loss function that would help the encoder give a consistent answer. And we want that encoder to be able to minimize this loss. And the problem, that we have is that in everything I've shown so far, I've given P, right? The thing is that when we start, we don't know P because we don't know the volume that we're looking for. We don't know the plane of symmetry. So we need a trick that would solve the problem without knowing the plane. If we knew the plane, we would just say, okay, just give the pose and it's symmetric, and we would be done with it. We don't know the plane. So we have to resort to some kind of trick, and that trick is basically the following. Instead of just minimizing the distance between an image and its predicted image for a pose, we basically we are going to build a library of images from that experimental image that we transform. And we are going to hope that among those images, the best answer will be present and that it will be consistent across. That's tough to believe, but that's the idea, right? So we generate new images from our given image. And we're going to hope that one of them, there will be one of them that will minimize the loss, and we're going to keep it. And we're going to hope that it will help be consistent in the hand. And with an H. I'm French, but in the hand, right? And so how do we do that? Okay, so if I repeat what I just said, if we knew the plane P that separate SO3 between the poses that correspond to looking at the object from above, S plus, versus the poses that correspond to looking at the object from below, so S minus, then we could basically say, okay, encoder, you're telling me phi, but also give me the symmetric of phi, and I will keep the best. There is no way we can do that because we don't know the plane. So all we can do is for any predicted pose from the encoder, generate a bunch of others, or actually generate a bunch of others from the data and ask the encoder which one is the closest to it. And among them, we hope that one of them will be always on the upside, for example, right? And so there are not a lot of ways to transform the data. All we can do is change the orientation or flip it, right? We don't, in one image, you don't have information about what's out of plane, right? All you can do is transform it by doing in-plane rotation or maybe flipping it as if you were looking at it from the other side, right? And that's not changing the information content of the image. It's just simple manipulation. So you can either rotate it or flip it, right? And this is the orbit that you have access to from your data. And so we are going to explore these orbits here. And in particular, if we just choose one, which is we just play with the in-plane rotation, and we even simplify it to asking to just rotate by pi, you end up with this loss function, which would be taking the minimum between the predicted image, the actual image, and the predicted one, or the rotated version of it. And you give both to the encoder. You predict two poses that you give both to the decoder. You end up with two predicted images, and you compare which one corresponds the most to the initial image. The one who wins, that's the one you remember, and that you use to backpropagate to update the encoder and the decoder. So that was the symmetric loss described in that paper. earlier this year from Axel. It's just one example of how you could do it that worked then. But everything I said before still holds, and you could try the other, like the flip and all that, and it should work. It's just that a matter of like which one would work better. It's not published in the paper, but the idea is there, right? So yeah, that's the gist of it. So the transformation we made to this autoencoder architecture is to replace the L2 loss with this symmetric loss, right? So that, I hope that was a little bit clear, because I hope it's more clear for you than it is for me. Okay, so that was one development. The other important development in our work, oh no, that's actually before I jump to the other thing. How does what I just say impact the actual training process? So we start training our architecture by starting with like a random volume, right? And then you start minimizing the loss. And if you take the L2 loss, what you will always end up with is this type of volume reconstructed where you can clearly see the planar symmetry. And it happened on some synthetic data set without noise that you could escape that and actually get to the actual answer. But in the presence of noise, you're almost always trapped there. So then if you turn on the symmetric loss, you see that you get to a better solution. You escape this local minima, get to a better solution. That's not symmetric. That's the gist of it. Okay, so another idea in this paper was how do you represent the volume, right? So traditionally, we think of volumes as, in Cryo-EM, as 3D maps with voxel values, like electrostatic potential intensity at given voxels. CryoDragon popularized neural net representation of volumes, and that showed the power of that. So here I want to talk about a slightly different representation that Axel came up with, which he calls a FourierNet. That's this guy here, which is actually two neural nets that work together. And the idea behind is that since we're in Fourier space, you actually have to cover a pretty big dynamic range. Like the low frequency signal is pretty strong. The high frequency signal is pretty low, right? It's often hidden in the noise. And having a neural net to cover this dynamic range is not trivial. If you take, yes?
In your loss, so here we're seeing that the power spectrum falls off. So in your loss, is it white noise, like each Fourier frequencies?
Yes, we haven't really played with other types of noise models yet.
I just wonder how it connects with this and the color.
Right. So for example, in Reliant and CryoSpark, you would have a different variance at different frequencies for the noise. Here we have the same across. It's a sigma square. We actually don't even have it because the way the loss is defined assumes white noise, the most boring white noise that you can think of. Yes, that would be interesting to investigate how that could impact the results indeed. But here it's more fundamental than that. Like the tool that the object that you use to represent the volume, does it have enough power to actually represent all the dynamic range that you need? And so if you use a siren here on this toy model in 2D, so a siren is like a neural net where each node is actually a sinusoidal instead of a ReLU or something like that. So it's well, you should check if you're interested. You should check the paper that describes it. But it's basically now a very well accepted way to define a neural net, and you see that it kind of fails at representing the whole range, right? And you can see in the real space that you actually lose a lot of signal, at least in the low frequency. So the FourierNet recovers most of it, and it helps also in the training process. So I haven't really shown what it was, except here. So basically, the reason it works is that if you think of an exponent, like basically of a complex number, you have the amplitude and the phase, and so basically one neural net here will encode the amplitude, and the other one will encode the phase, and that way you can really cover a wide range, right? It's basically an exponential representation of your signal. Yeah, so that's kind of the intuition behind it. So I wanted to mention that because that was also a great development from Axel, right? And so with that, you have the whole architecture, and that's the idea. So now, does it work? So here I'm showing simulated images. So again, we started with that, with some level of noise starting from a PDB file on the spliceosome and the spike from COVID, spike molecule. And essentially what we ended up with is a result that's very similar to what CryoSpark ab initio would give you. The difference being that CryoSpark is, as I said, going through a post-search approach, and we wanted to see how it compared. And so here, the experiment that we did, that we built a dataset of growing sizes, and we run CryoSpark on them, and we run cryoAI. And as soon as cryoAI reached 10 angstrom resolution, we stopped, right? Which means that if it reaches that resolution before it's in the whole data set, then it stops, right? And that's why we have this like constant price to pay with cryoAI versus a growing time for CryoSpark. And so you see that the amortization starts to pay off as your data sets become really big, right? So maybe it's not that advantageous for smaller data sets, but like if you start to really go for a very big data set, it's going to really help you. Yes?
So if I have another axis that is resolution, how should I think about it?
Yeah, that's a good question. I don't have the plot, but yeah, no, it would actually. I have one plot at the end. We can look at the. No, I don't. Okay, but it will take longer, right? I don't remember how it scales, but yeah, it's just because you have more pixels, right? In a way, so each iteration will have a higher computational cost, right? But yeah, we should look at that. Yeah. And here I'm just showing the training time, right? Which means how long does it take for the encoder to be trained? I'm not showing the time that it would take to evaluate the pose on all the data set. We have that, and it would be scaling similarly to CryoSpark, but right. So you still have to pay that price, right? Okay. So that was on synthetic data set. On real data, it's basically the same story. So it's basically a faster way to get to the similar result that you would get with CryoSpark. And there is a possibility that CryoSpark would take forever on a huge data set. And if you have that type of data set, maybe you want to consider an amortized approach. Okay. So, okay. So for I have a few more minutes. Maybe I'm out already. Okay. Sorry. So yeah, very quickly. That was for homogeneous reconstruction now. Or 30, how much, sorry? 10, okay, sorry. I need to work on that. Yeah, so I have time. All right, so once we got that working, obviously the question was, okay, how does it work on variable data sets? And we met Ellen, and so we started working on that together, and so Axel started implementing these ideas in sort of CryoDragon code, and now the problem is to solve this, right? So on top of assigning to each image a pose, you want to predict a latent variable that would encode the deformation of your volume, right? So the volume is not the same across the data set anymore. It will vary from image to image. And so the long story short is that 3DVA and CryoSpark would not amortize over poses, but it would not amortize either over conformations. what CryoDragon and CryoDragon 2 introduced is amortization over conformations, right? So everything I said about amortization today in cryoAI is the same concept that was implemented in CryoDragon, you know, right? So you would amortize over the z variable, the z latent variable. But then you would not amortize over the poses. cryoAI would do the counterpart, and so we put 1 and 1 together, and I think we got 2. Right, and so in terms of performances, I thought you might want to see that. So on a synthetic data set, so that's pretty small. You see that CryoDragon 2 and CryoFire, which is the name we gave to this method, would perform similarly in terms of training time, but the amortized approach would not be as accurate.
Could you tell us what those numbers are? I can't read it.
Oh, I'm so sorry. So they would take both about an hour and a half on 50,000 images and reach rotational accuracy. So CryoDragon would give below a degree, and CryoFire would give 2 degrees. Right? As you, so if you now go to 10 times this dataset size, CryoDragon 2 would now take 5 hours. CryoFire would still take 1 hour and a half. That's the same price to pay. Performances would still be in favor of CryoDragon 2. So amortization has a price in terms of accuracy. If you get to a 5 million dataset, CryoDragon 2 would take a day. CryoFire would still take below 2 hours, and the accuracy would start to improve slightly, right? So there is this trade-off to keep in mind. Like you get to an ab initio solution faster, but still an ab initio solution that may be slightly less as good than you would get with a more like post-search approach. So illustrating on what that means, like in terms of like, okay, how accurate are you on the conformation now? So we generated this like that synthetic dataset from the ribosome, generating a dataset with 2 rotation class, 3 or 10, and this is basically the prediction. So it works essentially. It's able to like identify the state that was originally put in the dataset. And on real data, it's basically giving sensibly the same result as CryoFire on this spliceosome dataset. And that's very similar to the ground truth. So yeah, if you want to hear more about this, I think Axel and Ellen will be at NeurIPS in New Orleans soon in December, presenting this. Please, yeah, if you go, please ask them and say that I did a terrible job explaining, so they need to explain again. Okay, so yeah, the future work can go in many directions. You've heard about atomic models or Gaussian mixture models coming in place, so we started to look into that direction. So just as a very short story, we have a little white paper on how we could use normal mode analysis for this, and so just as a little illustration here, we had these 3 different data sets that we generated. Basically, it's a transition across 2 conformations of the small protein. And we sampled 3 different distributions here. This is the ground truth. So if we give only 1 normal mode to deform the atomic model, we do a pretty terrible job. If we give more modes, then it starts to get much better. And we get like very close to the actual atomic model in the ground truth. So we are currently pushing that direction. So it's not working on real data yet. So yeah. That's one thing. And then, yeah, another thing that you might want to check out is okay, this field is exploding, and it's very hard. It's very easy to get lost in the latest development. How do they compare to one another? So we've in an effort led by Nina and Claire, we tried to like basically put all the different models and algorithms on the same foot and try to make it clear. So essentially, we came up with this. So maybe I'm not going to do it now, but like basically all the different flavors and modules and implementation that you can think of are coded here, and almost all the current methods have been assigned their little color, and so you can spend some time looking at this. It's a very dense and rich review, but it just came out in Journal of Structural Biology, so please check it out and tell us what you think. One of the main outcomes of that work was that we realized that there was a lack of validation and benchmark. I think everybody in the room agrees that we might want to push on that front because it's very hard to compare different methods to know, as a practitioner, which one is the best for my needs, etc. And so we are trying to start a little effort in that direction with like a shared organization on GitHub. So if you're interested, please reach out. At the moment, it's very early, but we have really hopes to basically make it a playground for developers to try their ideas and force benchmarking. All right, so I would like to thank all my collaborators over the years and founding, of course. And yeah, if you have any more questions, I'll be very happy to answer.